super for heavy and regular for light. There you go. Massive misunderstanding. Regular Fanny.
Pyrit kaikin keinoin hyvään suun terveyteen. Miten on vaihtoharjan laita? 3 kuukauden käytön jälkeen se alkaa olla loppuun kulunut. Puhdistusteho heikkenee ja plakkia alkaa kertyä. Uusi vaihtoharja takaa terveellisemmän puhdistuksen. Vaihda nyt. Oral-B. Anna sähköhammasharjasi tehdä työ.
Minski on hiljaa, minä teen töitä.
For this video, we turn our attention to a widely used class of pharmaceuticals called benzodiazepines, often called benzos for short. Benzodiazepines are depressants that enhance the effect of the neurotransmitter GABA at the GABA-A receptor, resulting in sedative, sleep-inducing, anti-anxiety, anticonvulsant, and muscle-relaxant properties. The first benzodiazepine was identified in 1955 and marketed only 5 years later in 1960. And by 1977, they were the most prescribed type of medication globally. But fast forward to 2024, and getting a benzo prescription is quite difficult for anxiety disorders, even though the effects of benzos are superior, as in most cases it completely removes anxiety. Currently, the class of medication called SSRIs are preferred, which gradually reduce anxiety without the relaxing, tolerance-building, and addictive properties of benzodiazepines. Still, pretty much all SSRIs can't compete with the complete removal of anxiety by benzos, which is why benzos are still used in more difficult cases and are very popular to purchase illicitly. Because they are so addictive and pose a risk for abuse, they have become scheduled drugs and are only available on prescription, though there is hesitancy to even prescribe them. But like most substance bans, this does not cover the whole class, and there are many benzos that are not banned. This also opens up the possibility for drug producers to legally produce and sell modified benzodiazepines that aren't listed as illegal. These are generally called designer drugs and are specifically made to circumvent these laws. Some examples include flunitrazolam, pinazolam, pyrazolam. Sometimes these are even completely new molecules that haven't even been described in literature or patents, like flunitrazolam, which is one of the most potent benzos known and is a strong muscle relaxant. The synthesis of benzodiazepines and the subsequent modification while maintaining activity and avoiding the law, however, is quite interesting. They are also a more challenging drug to make, compared to many other simpler drugs. So in this video, I will legally make flunitrazolam and see how difficult it is to synthesize on my first attempt. Most of the legal designer benzos contain a triazole ring, similar to the well-known Xanax. This extra ring increases the basicity and stability of this system, and also results in active compounds with higher affinity to the benzodiazepine receptors. Benzodiazepines can be made from the amine benzophenone precursors. Many of these are also precursors for other molecules, and so they are generally available for purchase without having to go through the trouble of synthesizing them. However, some are not available, and constructing these benzophenones can be quite annoying, expensive, and the yields are subpar at best. For example, the precursor to the benzo pinazolam, containing a nitro group and a pyridine, is not available online, or at least not for a normal, worthwhile price, which is the benzo I originally wanted to make, as its effects are more desirable than flunitrazolam. So that would mean the precursor for pinazolam has to be self-constructed. Since that's very annoying, I chose to go for flunitrazolam, of which the precursor is available, and it also doesn't produce illegal intermediates like some others. So to get started, I set up a flask with a stirrer in a water bath and add in 270 ml of the solvent dichloromethane. As the first reagent, I add in 25 grams of 2-amino-5-nitrophenyl 2-fluorophenylmethanol. Then as the base, I add in 16.1 grams of sodium bicarbonate, but organic bases like triethylamine are also fine. I now fill the water bath with ice to cool it down and keep the temperature around or below room temperature. I also wash out the funnel with some more solvent. I then attach an adapter and a small dropping funnel, and into the dropping funnel I pour 11.5 ml of the reagent chloroacetyl chloride. I slowly drip this into the flask to prevent the temperature from increasing too fast. And when the addition is done, I leave it stirring for 4 hours. What happens is a typical reaction of an amine with an acid chloride in the presence of a base, to form the corresponding amide. How it proceeds is first through nucleophilic attack of the amine onto the acid chloride carbon, of which a pair of carbonyl bond electrons moves onto the oxygen. The protonated intermediate is deprotonated by the base sodium bicarbonate, which then falls apart into CO2 and water. The electron pair on the oxygen then returns to form a double bond, and in the process kicks off the adjacent chlorine, as it is a good leaving group and will gladly take these bond electrons, which goes on to form sodium chloride with the remaining sodium ion, and giving the final amide product. When it is all done, I drip in a bunch of water to destroy excess chloroacetyl chloride and dissolve excess base and salts. Then to make all the solid product dissolve, I add in more dichloromethane and let it stir for a while. When that's done, I move it all to a separatory funnel and separate the layers. I discard the upper water layer and then wash the DCM layer once with a sodium bicarbonate solution. In this case, I just dump in the sodium bicarbonate directly, because I'm too lazy to dissolve it separately. I take the washed DCM layer and I've put it all in this flask. Now to remove remaining droplets of water, I add in some sodium sulfate, which will absorb them. To remove the sodium sulfate again, I filter it through some cotton into a flask, which I set up for vacuum distillation, to distill off all the solvent. When that's done, a mostly yellow solid is left behind, along with some orange crab. It could potentially be recrystallized to see if the orange stuff can be removed, but I decided to continue as it didn't seem too significant. In the end, the yield turned out to be 25 grams, which is 77%, and that's alright. I will use all the material directly for the next step. So for that, I set up a large flask in a heating mantle, and first add in 24 grams of hexamine as a base and catalyst. Then as an ammonia source and reagent, 10 grams of ammonium chloride. Using ammonium acetate is better here, but I didn't have any on hand. As the solvent, I add 750 ml of ethanol. And finally, all of the previous product, along with some extra ethanol. I then attach a condenser and reflux this mixture overnight. What happens in this reaction is a cyclization to form the benzodiazepine. How it proceeds is first a nucleophilic attack of hexamine onto the carbon adjacent to the chlorine, kicking off the chlorine and forming this tertiary ammonium salt. This tertiary ammonium salt is attacked more conveniently by the ammonia, and so can produce the corresponding primary amine, which is deprotonated by a hexamine molecule. Amines can attack ketones to form imines, and so this amine will attack the ketone intramolecularly, giving a cyclized intermediate that undergoes a proton transfer. The resulting amino alcohol quickly eliminates water to form the imine, giving the benzodiazepine product called desmethylfluticrazepam. When I come back the next day, the mixture has become an unfortunate dark red. So we'll see what it is. I immediately set this up for distillation to remove the solvent, and when it is mostly gone, some red tar remains. The product should be inside, so I have to try to get it out. First, I will remove salts by partitioning it between water and dichloromethane. I bring it to the separatory funnel and separate these layers. I extract the water layer once with dichloromethane to make sure some of the product isn't lost inside, and I then discard the water. To the dichloromethane layer, I add some sodium sulfate like earlier to dry it. I filter this through some cotton and then distill off the solvent. I am still left with some tar, and to get out the product I have to precipitate out the tar before the product precipitates. And I can do so by mixing hexane and dichloromethane, boiling it and increasing the hexane concentration until the red tar precipitates out. At a certain point, the solution becomes yellow, but no product precipitates yet. Only a thick red liquid slowly settles out to the bottom. I thought it was fully liquid, so I wanted to separate it in the separatory funnel, but the tar quickly solidified. And when the solution started to cool down, the product started to crystallize out as well. So I quickly decanted off the yellow liquid and dissolved the remaining product and tar in the funnel with some DCM. I repeat the exact same process on this mixture, and after letting the dichloromethane solution with the product sit in the freezer, it crystallizes out as a yellow-orange solid. I collect the solid with vacuum filtration and wash it with more hexane. Still, I am not fully satisfied with the color of this material, as it should be more yellow and not so orange. So I repeated the exact same procedure, and more red tar that was inside was removed. And afterward the product looks more yellow. The material is still wet from the solvents, so I bring it all into a flask in a heating mantle and heat it to 50°C while pulling a strong vacuum. this will pull out all of the remaining solvent. After leaving it overnight, I am left with a dry and very yellow powder. The weight turned out to be 5.25 grams, which is a yield of 24%. And honestly, I am fine with that, considering I used less hexamine and ammonium chloride is not so optimal for this reaction.
Avaa kotiovi kännykällä. J-Linus älylukko. Myös kerrostalo kotiin.
Anyhow, I took a sample for future analysis and used the rest for the next reaction. Now, for the construction of the triazole, there are essentially three methods that I came across that seem to be in use. The first one is one I can't use, but I still wanted to show it because it's kind of ridiculous. It has many steps, and this oxidation step only has a 23% yield, so that doesn't seem so great. However, it was used in the past for the synthesis of Xanax. Anyhow, one viable route is transforming the carbonyl into a thiocarbonyl, allowing for nucleophilic attack by hydrazine, which can then ring close with triethyl orthoacetate to form the desired triazole. This seemed to be the most common route, but the yields aren't that great, and using Lawasson's reagent is very dirty, only reaching about 50% conversion to the thiocarbonyl in literature. So that means I will probably get 10%. The last one has the least steps and seemed the most convenient to me. However, it's a bit unique. A weird diamorpholinophosphonyl chloride reagent is used, which apparently seems to be a fair leading and convenient for making these triazoles. So that is the one I want to try, as I also have the stuff to make the phosphorus reagent, and so that is what I have to do first. For that, I set up a large phenolic flask in a water bath, add an ice, and attach a thermometer. I then add in 330 ml of the solvent xylenes. Ideally, toluene or even benzene should be used, but I happen to have run out, so this will have to do. As the first reagent, I add in 31.5 ml of phosphorus oxychloride. I then attach a dropping funnel to the flask, and into that I pour 170 ml of the base and reagent morpholine. I slowly drip this into the flask while keeping it below room temperature. In this reaction, phosphorus oxychloride reacts with morpholine to form the reagent that I need, dimorpholinophosphonyl chloride. How it proceeds is first through nucleophilic attack of the morpholinamine onto the phosphorus, forcing a pair of bond electrons onto the oxygen. The protonated intermediate is deprotonated by another morpholine molecule, after which the electron pair on the oxygen returns to form a double bond, kicking off a chlorine ion that goes on to form morpholine hydrochloride. This exact reaction happens again to attach a second morpholine molecule, but it doesn't happen for a third time since I added 4 equivalents of morpholine, so by then it is used up. When the addition is complete, it is completely white from suspended morpholine hydrochloride. I then take it out of the ice bath and let it stir at room temperature for 3 more hours to ensure completion of the reaction. After that, I set it up for vacuum filtration to remove the insoluble salt, which I wash with more xylenes to get out the product. I discard the salt, but theoretically it can be transformed back to morpholine if desired. However, it's not so expensive. I take the filtrate with the product and move it all to a flask in a heating mantle. I vacuum distill off most of the xylenes, and when it's more concentrated, an insoluble gum is supposed to form that has to be removed with filtration. I see some crap is stuck to the walls of the flask, so I separate the liquid from the crap by filtering it. It is now a more yellowish solution instead of red, which is good, and I can use this hot solution directly to precipitate out the product. For that, I only have to add in some cyclohexane, and the product settles out as an oil. It's not supposed to be an oil, so we have to force it to solidify, which can be done by stirring it strongly in the anti-solvent. After a short while of stirring, it all solidified and the color became a lot better. And to collect the product, I filter it again and wash it with the solvent hexane to remove remaining xylene, which is difficult to drive off under vacuum, and maybe some impurities will also go away. When that's done, I take the filter and scrape all the product off and move it to a large flask in a heating mantle.
Mitä?
I attach a vacuum adapter, heat it to 50C and pull a strong vacuum. This should pull out all the remaining hexane and give the dry product. I leave that overnight to make sure it is fully dry, and when I return, it looks the same, but it should now be good to go. In the end, I am left with 40 grams of the product dimorpholinophosphonyl chloride. It's less than literature, but I used a different solvent, which might impact the yield. More can supposedly be recovered from the mother liquor, but it's not necessary for me since I have enough. Now that that's done, I can return to the benzo I made before and continue with the next reaction. For that, I add 4.86 grams of the desmethylfluornitrazepam that I made to a 3-night flask. I dissolve it all in about 200 ml of the solvent tetrahydrofuran that I dried with molecular sieves. I attach a nitrogen line to the flask and continuously blow nitrogen through it. When it is all dissolved, I add 0.72 grams of a sodium hydride dispersion. It immediately reacts and forms a bunch of hydrogen that bubbles out. When the bubbling stops, the required intermediate has formed, and I can then add 5 grams of the dimorpholino phosphonochloride that I made. I then leave this to stir under nitrogen at room temperature for 4 hours. In this reaction, the benzo reacts with sodium hydride and the phosphonochloride reagent, producing this phosphorylated product. How it proceeds is first through deprotonation of the lactam nitrogen by sodium hydride, forming hydrogen, which bubbles out of solution. This deprotonated lactam forms a preferred form on which the electron pair resides on the oxygen. It can be considered an alkoxide, which is known to be nucleophilic, so the oxygen can attack the phosphino reagent in a manner analogous to when the reagent was made. The double bond returns and kicks off a chlorine ion, giving sodium chloride and the final phosphorylated product. Unlike an amide, this new group can undergo nucleophilic attack and is conveniently kicked off, so that we can construct a triazyl ring. It can also undergo hydrolysis back to the amide, although not too quick, but water should preferably be avoided. When the reaction is finished, I remove all the adapters and quickly filter it through some cotton to remove insoluble salts.
Hiljaa.
After that, I distill off all the THF under vacuum. This gives some crap, and it is possible to isolate the phosphorylated product, but I immediately use it to continue with the next reaction. For that, I need N-butanol, but I only have the next best thing, which is isobutanol, so I will use that. There is no mention why butanol is used, so I assume other alcohol solvents are fine, but you never know. I then add in 2.4 grams of the reagent acid hydroside.
Heti 12 aikaa me päästään ja sit 1 tuut
In this
vasta vähän
reaction, the
myöhemmin. Pitää
phosphorylated
nukkua vielä ja
product reacts with acid
syödäkin
hydroside
vielä
to form
pitää.
flunitrazepam. How it
tyhjällä
proceeds is
maalla.
first through nucleophilic attack of the hydroside with its carbon, of which the carbon-oxygen bond electrons move onto the oxygen. This dimorpholino phosphate then deprotonates the intermediate to give the dimorpholino phosphoric acid, which might continue to aid in protonation and deprotonation of the intermediates. We are then left with this intermediate that shows tautomerization with its imine, where the double bond can move from one nitrogen to the other. This hydroside might also tautomerize to the azine, potentially allowing an easier path for attack. When the ring-borne amine is freed up, it can perform nucleophilic attack, although this reaction is likely to be slow, since it is intermolecular and limited by sterics. Either way, when the amine attacks, a cyclic intermediate forms that undergoes a proton transfer between the amines, leaving an amino alcohol that quickly eliminates water to transform into a triazole, giving the final product flunitrazolate.
Brown Skin Eye Expert IPL. Tämä on maailman ensimmäinen IPL-laite, joka oppii. Kokonainen vuosi ilman pistelevää sänkeä on nyt kätteni ulottuvilla. Vähemmän arvailua, enemmän hoitolatason tuloksia. Vain 15 minuuttia ja valmista tuli. Brown IPL.
Just to have fun with it and always stay true to what you feel most confident in.
When I return the next day, the mixture has become more red, so at least something happened. I then immediately distill off the bulk of the solvent and add water to dissolve remaining solvent, and whatever crap can dissolve into it. I then add a bunch of dichloromethane, in which the product will dissolve, and unfortunately the tar as well. I then separate these layers in the separatory funnel and discard the water layer. I wash the dichloromethane layer once more with water, and then filter all of it through cotton. Now I will try and repeat the same workup that I did before, where I add hexane to precipitate out the tar. But first, I concentrated the solution a bit by distilling off some DCM. I then move that to a crystallizing dish and heat the mixture to a boil. I then gradually add hexane to it until it seems stuff precipitates. After setting it in the freezer, the solution is more red and some brown tar is precipitated. I filter that off with vacuum filtration through a glass frit, and then move the orange-red filtrate to another flask in a heating mantle to concentrate it further. In the end, I found out that it was too difficult to separate the tar from the product with this mixture. In some literature, they say it might precipitate by adding ether instead of hexane, but I ran out, so I will instead do column chromatography, which can separate components based on their polarity. For that, I first dissolve it all back into dichloromethane and mixed it with some sea light, which will lightly hold on to the product and give an easy to handle powder. When that's done, I set up a column and weigh out 200 grams of silica gel, of which I make a slurry with the eluent, which is 50% ethyl acetate in hexane. I pour it all down the column, let it pack, and put a protective layer of sand on top.
Naama taas
I then
eessä.
put on the sea light
Sorry.
product mixture,
This
wet it
is
with the
my
eluent, and
content.
put another
It's
layer of sand
the
on top.
real
The product
shit.
easily runs off the sea light and into the
Over
silica.
the
I run the
board
column
of the
normally by applying light air
Atlantic
pressure on top to force the
Sea,
liquid through faster. The yellow product runs off as one of the
also
first
known
components,
as
while the very
Finnish
colored impurities stay on
people,
top. When it's
discovered
finished,
the
I collected a bunch of
fucking new
fractions.
part
These are
of
fractions that came later that have an
USA
orange
of
impurity that becomes
America.
darker on standing in air.
601
The
päin
first fractions I
helvettiin
collected
täällä
are yellow,
kaikki.
and I checked with TLC to see their components, and they contain what I assume is my product.
Nyt se on paljastettu.
After distilling off all the solvent and drying the material under vacuum, I am left with a greenish yellow solid. But it seems this contains two components with very similar polarity. To try to get some more crystallized and pure yellow product, I will repeat the same procedure as earlier, where I dissolve it in DCM, add hexane, and put it in the freezer. Some stuff precipitated out, and it seems the impurity must be sank and is stuck to the bottom, while the product crystals are floating more freely. So I will just filter it to collect the yellow material, while I ignore the rest that's in the dish, as it's more green, as the product should be yellow. I scrape everything off the filter and put it in a container. In the end, I am left with approximately 30 milligrams of product, which is an amazing and professional yield of 0.5%. And honestly, I'll take it. For doing it the first time. There are definitely improvements to be made in the procedure, as I deviated from the literature as well. Now, it is still an assumption that this is my product, so I will get it analyzed with NMR later. Anyhow, we see that it is still a challenge to produce the product, and the yields of multiple steps can be quite poor, giving quite little material. That was it, see ya.
How it works? How it works? No, the video is over. Oh, chica booyah.